All right, today we're going to start with transformations. So we introduced you to all the parent functions last time, and then now we're going to do transformations. All of the parent functions are transformed in the same exact way. They all have a transformational form of the equation. This is an example of the absolute value one because it's got absolute value bars right here. But we could change those absolute value bars and do a squared right here, and we would be talking about the quadratic. We could change these absolute value bars to the square root, and we would be talking about the square root transformational form. Change it to a cube, and we would be talking about the cube root. So all of the transformational form functions are taking the parent function and doing certain transformations, and they all have A, B, C, and D here. Each one of these does something different to the graph. In Algebra 2, we'll mostly focus on A, C, and D because B doesn't make as much sense with our Algebra 2 functions. When you get to pre-cal, though, B will make a lot of sense with those functions that you deal with there. To start us off, I'm going to go ahead and share my screen here for the calculator. Here is our Desmos calculator, and I've gone ahead and done the absolute value, which is the one that we were looking at there. It is right here um, on our first thing. And then I've included sliders for A, C, and D. So A, C, and D right here, which are the ones that we told you. Now, as I move this A value, notice what's happening to our graph. So it was a lot more narrow here as I go higher in the number, and then as I go lower in the number, it gets wider. Now, if I went into the negative values, so here we are at a really small number, so there's 1/2. Our graph is rather wide. I keep going down and I go into our negative numbers. Look what happens when we do our negative there on that A value. It flips over. Let me take these back to 0 so you can see it from the parent function. All right, so there's the parent function, and I've only moved the slider now for A to be negative. As I move it to a more negative number, you'll notice that it continues to get narrow just upside down. And as I move it to the bigger number, we'll come back up and it gets narrow, but to the top. All right, so let's go back to 1 here. So we're not going to change the A value at all. We're going to leave it at 1. So this is the absolute value parent function. We're going to look at our C value now. That's the one inside of the X here. As I move it to the right, my slider to the right, it also moves to the right. So when I put a positive number into this C value, like 4, it moved to the right 4. As I keep going, it's going to move even further to the right. Now, as I move to a negative number, then it has moved to the left from my parent function. Let's keep in mind here that if we look at our equation, this is x minus c. So if I put in this negative 6.1, that would turn into a plus c. It would be x plus 6.1. And that moved it to the left. So you want to keep that in mind as you do transformations. Now, as we bring it back over to the right here, and I make it back to 0, we're back to our parent function. The last transformation, our D slider here, it is at 0 right now. If I move it to the right and I find a positive D value, notice that my graph is completely picked up and moved up. And then as I move down, it is moved down on the graph. So -4 brought it down 4 from the parent function. These are the transformations that you will see on all of the functions all year. So let's just reiterate. I'll take that back over to 0 so we can summarize those findings and write those down. Sorry, put that at 1. There we go. When I changed A to a big number, it made it narrow. When I changed it to a smaller number, it made it wider. When I changed it to a negative, it flipped it completely upside down. All right, so let's go back to our 1 on that one. When I change C to a positive number, it goes to the right. When I change it to a negative number, it goes to the left. And then our last one, our D, when it goes up, it goes and down. All right, the next thing I want to show you, in this case, I've gone ahead and put two functions. So on the top one here, I've got our absolute value. On the bottom one, I have our quadratic. Two functions that you're sort of familiar with just so that you can see. Again, if I move my A, it's going to get narrow. Notice they're both doing the same thing. So it doesn't matter which parent function you do. When that A value gets bigger, it gets more narrow. We call that a vertical stretch. When we make it a smaller number, it gets wider, whether we're talking about the quadratic or the absolute value. That's called a vertical compression. Looks like you took it from the top and just kind of squished. If we change our C value, notice they both change. So it doesn't matter which parent function we're talking about, the transformations will do the same on all of our parent functions. And again, with our D up and down. Okay, so let's go back to our notes and summarize that so that you can see what we are talking about here. All right, so let's summarize what we found. The A value, the one that's being multiplied in the front, when it was greater than 1, it caused a vertical stretch by that A value. So vertical stretch looks like you took it from the top and the bottom and you pulled. That's why we call it a vertical stretch. We're taking it from up and down and we are pulling. So it gets it more narrow. All right, between 0 and 1, so a fraction caused a vertical compression. Again, by the A value. So that one looks like we took it from the top and we squished down, so it got wider. And then when the A value was negative, it caused a reflection across the Y. I'm sorry, across the x-axis, flipped it upside down. Again, that's going to be true for all functions. We're using this absolute value one because we are in the absolute value unit, but that is going to be true for all of the parent functions. That is what A is going to do. For B, that's inside the operation. So that's going to be inside the squared or inside the square root, inside any of those. That's where we're going to find our B. And it kind of does the opposite as this one here. So when B is greater than 1, it causes a horizontal compression by 1 over B. That's the reason. So if it was 3, for example, the horizontal compression would be by 1/3. So that scale factor is a fraction. That's the reason why it's causing the compression. Now it is horizontal, so it looks like we're taking it from over here and squishing this way, the horizontal compression. All right, so when it is between 0 and 1, it causes a horizontal stretch by 1 over B. And so horizontal stretch, we took it over here and we moved it this way. A horizontal stretch looks very similar to a vertical compression because horizontal, you're stretching this way, vertical, you're squishing this way. It's going to do the same thing to the graph. That's the reason why it doesn't make a lot of sense here in the Algebra 2 functions. It will make a lot of sense when you get to the pre-cal ones because they are significantly different. Even though these functions look the same, the pre-cal ones do not. All right, and then the negative causes a reflection across the Y. All right, the next one is the C. It's the one that you're adding or subtracting to the X. The main formula is minus, so when we put a positive C here, it is going to stay as X minus C. For example, X minus 2 or X minus 3 or X minus 4. That causes our graph to go to the right C. When it turns to X plus C, that means the C was negative, and a minus negative turns into a plus there. And so that would be like a -2. If we placed a -2 here, the minus and the negative would cancel out and turn into a plus. That's when it goes to the left C. And then a positive D goes up and a negative D goes down. All right, so why are transformations so important? Well, it makes graphing all of the parent functions with transformations super easy. If I know that parent function that I studied last time from the intro on parent functions, and I know the transformations, then I'm able to graph it without a calculator. without anything, really. So we're going to practice some of those right here. This first one is just the parent function. So let's remember what that looked like from our last lesson. Absolute value, that was the V shape. It was two lines basically. So we had a line, the same as a linear parent function in this first quadrant. And then where it would have gone into the negative, it turned it into the positive for the absolute value. So it looks like this. Our vertex there is at 0, 0, that point right there. Our domain was all real numbers. And our range went from 0 to infinity, including 0. Now notice it says slopes. This is going up 1 over 1, up 1 over 1, up 1 over 1. That's what slope is. It's that rise over the run, the difference in our y's over the difference in our x's. You'll hear it in a lot of different ways, but that's what it is. And so our slope we represent usually as m. And so it is a positive 1 when we go this way. Now it's a negative 1 on this side because it's going down 1 and to the right 1, down 1 to the right 1. So this has a slope of 1 on the right-hand side and a slope of negative 1 on the left-hand side. And we'll use that as we move forward on these. All right, so on this second one, we've got our absolute value parent function again, because that's the operation that's happening here. But this one has an x plus 3 here. We said when it's x plus 3, it goes to the left 3. So instead of having my vertex at 0, 0, I would go to the left 3. And I would do the same exact thing to every single point here. It would go to the left 3. So I could take this next point and move to the left 3. So it's right here, left 1, 2, 3, and there it is. I can use my slopes of 1 and negative 1 to create the rest of the graph as well, going up 1 over 1, up 1 over 1. So you've got two different ways that you can graph that. But there's my new graph, and I did not use a calculator for that. We were able to graph it by knowing the parent function and knowing the transformations. My vertex is at negative 3, 0. My domain is still all real numbers. My range is still from 0 to infinity because I did not go up or down. I'm still at 0 for that y. And we said this went to the left 3. All right, for my next one, this minus 5 is outside of the absolute value bars. That tells me it is the d value. D is the one that is on the outside of the operation. So this is on the outside of the operation. So that is going to go down 5 units because it is a minus 5. So down. We forgot to write the d there. So our parent function, again, starts right here at 0, 0. So it would be right here. It is going to go down 5. So now the vertex is right here at 0, negative 5. I can do the same thing to every point. So the point that was at 1, 1, I go down 1, 2, 3, 4, and 5. The one that was at negative 1, 1, I go down 5. And so there's the start of the V shape. Or I can use my slopes. Go up 1 over 1, up 1 over 1 to create that right side. And then on the left side, it's down 1 and over 1. And so there is my graph. My domain has not changed. It was all real numbers, so it stays all real numbers. My range on this one did change because now I have y values that are lower than 0. My smallest y value here is negative 5. So this should start at negative 5. There is a point there, so I'm going to have a bracket, and it goes up forever, so that would be infinity. All right, let's look at a couple more of these now with the combination of different transformations. And I'll let you try this one, but I'll go ahead and do these two with you as well. For this one, I've got 3 different transformations here. So this is a negative where the place of the a is. And so we said when we have that, that is a reflection across the x. Then we have an x minus 3 on the inside. We said that's right 3. And then the last one is the plus 2. That is on the outside of the operation, so that is up 2. So we're going to start with our parent function that was right here. Now this can't reflect over the x-axis because it is on the x-axis. And then it's going to go to the right 3 and up 2. So here is my new vertex at 3, 2. Notice that's the C and D value. That's going to be true every single time. So the vertex is always that C and D value. The next point over would be 1, 1 right here. The first transformation I do is reflected over the x-axis. You have to do reflections first, then stretches and compressions, then the horizontal movements and the vertical movements. You do have to go in that order or it's going to mess you up. So 1, 1 reflects over the x-axis, then it goes to the right, 1, 2, 3, and up 1, 2. And so there's my next point. The one that was at negative 1, 1, I reflect it over the x-axis. I go to the right, 1, 2, 3, and up 1, 2. And so there is my graph. In all of the graphs that we've looked at so far, they have not gotten wider or more narrow. They have stayed as the parent function since we had no a value number. So now let's get the domain and range going for this one. Our domain is still all real numbers because this is going to the left and right forever. So with absolute values, that's basically the domain every single time unless they're restricting it. The range, however, is coming from negative infinity because it's coming from down here up to this biggest point of 2. So this would be negative infinity to 2. We do have a point at 2, so we're going to have a bracket there. All right, for 6, that's the trickiest one you're going to get. One of the things you're going to have to recognize on this transformation equation, the b is factored out. There should be nothing in front of the x when it is in the correct transformational form. So they can trick you and give you the equation in this format right here, but you don't want to be tricked. That is not the transformational form. To get it in the transformational form, we have to factor out whatever's in front of the x. In this case, that's a negative. And so a negative times x gives me negative x, and a negative times a positive 3 gives me a negative 3. Then I close my absolute value bars and I have my plus 2. That is the correct transformational form. When it is not in the correct transformational form, you cannot start pulling transformations from it. But now that it's in the correct format, now we can pull the transformations. So the first one is that reflection across the y. When you write these transformations, make sure you write the entire thing because there is a difference between reflecting across the x-axis and reflecting across the y. Across the x is on the outside of the operation in the place of a. Reflecting across the y is on the inside of the operation. That's the b one. Then we also have a left 3 and an up 2. So we've got 3 transformations on this one as well. Transformations always come first. I'm sorry, the reflections come first. So our vertex is right here at 0, 0. Now it is on the y-axis, so I cannot reflect that across the y-axis, but I can move it to the left 3 and up 2. My next point that's 1, 1 would be right here. When I reflect that across the y-axis, it lands right on negative 1, 1. If you remember, that was also a parent function point. Then I move it to the left 3 and up 2, and I'm right here. This reflection across the y-axis, you're not even going to notice it on the absolute value function. Let's go up before we finish this one and think about that. If I reflect across the y, this line right here is going to be right here. And then this one, when I reflect it across the y, is going to be on this side. So they're kind of switching places. A reflection across the y, you're folding right there. Well, this part lands on this one and this one lands here, so you do not see it. It's happening, but you don't see the difference. So this graph right here, again, is going to go this way and this way. It is not any thinner or any wider because there is no a value here changing its stretch or compression. Our domain is still all real numbers, and our range is from 2 to infinity. There is a point at 2. We had forgotten to write our vertex here. It is at negative 3 and 2. Remember that vertex is coming from these two always. So my C value here is negative 3. My D value is positive 2, so that is the vertex C comma D. Hopefully you notice that that D value also comes in handy for our range. The D is always going to be part of the range, either coming from negative infinity to D or from D to positive infinity. All right, pause the video and you try the two right here. Go ahead and graph number 4 and check if you've done it correctly. Here's what you should have gotten. The vertex is at 3, 2 because it went to the right 3 and up 2. No stretches or compression, so we're going to have it the same width as that parent function. All right, let's head on over to the back and talk about now some of those stretches and compressions because that's probably the hardest transformation to do. So this first one here has a vertical stretch. This is bigger than 1, so that is a vertical stretch by 3. Then we have a right 2 and a down 4. So there is all my transformations on this one. The vertex is still going to be at that 2, negative 4. Since our vertex is at 0, the only things that are going to affect it are those two right there. So right 2 and down 4, there's the vertex. All right, so let's talk about what happens when we do this vertical stretch of 3. So again, a vertical stretch goes like this, and we multiply it up. There's a couple of different ways we can do that. So the next point over is supposed to go over 1 and up 1. Because of the vertical stretch, it would go over 1 and up 3. We multiply that y value times 3. Same thing's going to happen on this side. That's what makes it that really narrow graph. Again, I took it from the bottom and the top, and I went this way so it gets more narrow. You can also think about the slopes are being multiplied times that. So our slopes here are a positive and a negative 3. And so I go up 1, 2, 3 and over 1, up 1, 2, 3 and over 1, instead of the up 1 over 1 like the parent function does. And so there is our graph. All right, this one's got 4 transformations. That's hard. There's a lot of them there. Our vertex is at negative 2, 3, because that's the C and D value. And now let's talk about all these transformations. The first one is a reflection across x-axis, because that is the A value. We have a negative there. Then we have a vertical compression by 1/2, a left 2, and an up 3. All right, so our vertex is at negative 2, 3, so that's going to be our starting point right there. Now we can think about the negative as a reflection across the x-axis, so it's going to go downward. That's what that negative does. Remember, it starts when it's at 0, 0. Instead of going here, it's going to go down here, so it's going to flip it upside down. And then the 1/2 is going to make it wider. And so that becomes the slope right there. Instead of going up 1 and over 1, we would go up 1 and over 2 if it was just 1/2. Since it's negative, we're going to go down 1 and to the right 2. And 1 and 2 right there. So the slope is that 1/2. The absolute value works very similar to 2 lines. And so we have a wider graph that is now turned upside down. My domain is still negative infinity to infinity, and I forgot to write that here. This one was from negative 4 to infinity because it went up. That should be a bracket. For the range on this one, we're coming from negative infinity and going up to 3. And so that's a bracket there because it does include that 3. That one had 4 transformations. That's a lot. That's probably more than we'll give you, but that would be the max if we did. All right, the next one is the same concept, except it has a square here. That tells me I start with the quadratic parent function instead of the absolute value one, the one that's like a U. Our next one is also quadratic, and then we've got 2 square root functions. I'm going to let you guys try those so that you can see the different functions and come back and see them, but I'll do one or two with you. So I'm going to do this number 10 with you. It's a quadratic and it too has a vertical stretch by 2. So our vertex would be at 3, -1. So 3, -1 right here. It is flipped over the x-axis because we've got a negative there. So let's write those down. Reflect across x-axis. It's got a vertical stretch by 2. And then it's got a right 3 and a down 1. All right, so our parent function looks like this. The negative is going to make it upside down. So it would go this way. We're going to be concave down. The 2 causes the vertical stretch, and then the right 3 and down 1. By moving the vertex there, I've taken care of really this part right here. Now, instead of going 1 and 1 like the parent function does, it would go 1 and 2 because that vertical stretch is multiplying those y values times 2. Instead of going over 2 and 4, it would go to 8. And so we end up with a quadratic that looks like this. And so what I'm saying when I say those numbers, remember the parent function was -1, 1, 0, 0, and 1, 1. We talked about these on the last introduction to parent functions. So these are the parent function key points. When I do this 2 here, this vertical stretch by 2, I am multiplying the y values times 2. So our x's here stay the same because this is a vertical stretch, so it's dealing with the y's. But our y values multiply times 2, and so we get that vertical stretch there. So to go from the parent to this new one, that's the 2. Now, since there's the negative, we're actually multiplying times -2, so this would become negative and this would become negative. All right, one more with you guys. I'll go ahead and do this square root function one. The square root one, if you remember what that looks like, it looks like this. And so we need to move that to the right 2 and down 2. And so our vertex was at 0, 0. We're going to move it to the right 2 and down 2. So my vertex is right here. The key points for the square root one were 0, 0, 1, 1, and 4, 2. So from this new point, I can go over 1, up 1, and there's my next point, and over 4 and up 2, and there's the curve. I could do that because there was no stretch or compression, so it's the same exact size as the parent function. It is just moved over 2 and down 2. The rest of the graph looks exactly the same since there's no stretch or compression. We did forget to fill out that domain again. That was -infinity to infinity, and this is -infinity to -1. Notice again that d value. So our vertex came from the CD, and that d value is still part of that range. So keep that in mind. For our square root one here, our vertex was at 2, -2. And so our domain started at 2 and went on forever. And our range started at -2 and went on forever. All right, go ahead and pause the video and do that 9 and 12 so that you guys can check and verify that you can graph those without a calculator. We've been doing it without a calculator this entire time. You're using that knowledge of that parent function that you studied from the day before and your knowledge of transformations. Come back and check your answers. All right, so here they are. My quadratic, it's moved to the left 1 and up 2. So it looks like this, left 1, up 2. Everything else is still the same from the parent function. There's our vertex and our domain and range. All right, for number 12, we had a reflection across the x-axis, a left 2 and an up 4. And so our vertex that goes right here went to the left 2 and up 4. The point that was at 1, 1 reflected over the x-axis, moved to the left 2 and up 4, and so we get the curve facing downward this time. So that did change my range to negative infinity to 4. Now my domain is still from -2 to infinity because my first x value here is -2 and it goes forever to the right. So there is our transformations. Again, those transformations are useful for all of the parent functions. They do the same thing. You just start with the whatever parent function the operation is on.